Today, I'll demonstrate how my project EEG-based emotion recognition for mental health support works. In today's fast-paced education and workplace environments, stress, emotional fatigue, and loss of focus have become significant issues that affect productivity, well-being, and mental health. To address these challenges, I designed a system that uses EEG signals to detect emotional states and offer personalized mental health interventions. My approach uses advanced machine learning, specifically deep neural networks, to classify emotions such as happiness, sadness, fear, and neutrality. I'm using the SEED4 dataset to extract relevant features from EEG signals. These features then train a CNN, which accurately predicts emotional states from EEG data. After training, I deploy the CNN model inside an API. This API connects with a user-friendly front-end interface. Users simply just upload their EEG data and the system uses the trained model to predict emotion, providing immediate contextual feedback and practical suggestions to help manage or improve their mental well-being. My project has four main components: the EEG feature extraction pipeline, deep CNN model training, API inference service, and the front-end interface. In this video, I'll walk you through each component step by step, starting now with the first component, the EEG feature extraction pipeline. First, I mount the Google Drive. Here I have saved the SEED4 dataset, so this let me access the EEG files directly inside Colab. This is just a helper function which clears up the variables I'm not using, and this just helps to free up RAM. Here I'm importing all the libraries I need. This includes tools for signal processing, working with EEG files, generating spectrograms, deep learning, and plotting results. To monitor the pipeline's performance, I wrote a small timer function that wraps around other functions and prints how long they take to run. It's just a quick way for me to check the performance of each part of the pipeline. In this part, I create a dictionary that stores the emotion levels for each experiment sessions in the SEED4 database. These levels are neutral, sad, fear, and happy, and are directly taken from the SEED4 database README file and are used later to tag each EEG recording with the right emotion. Here I'm just setting up a config dictionary to keep all the main settings in place, like file paths, spectrogram details, and mode operations. I have compared a few pre-trained models for embedding purpose. Inception v3 worked best for my case, so I'm using this function to store its URL and output size. I added two debug options, one to run a smaller, faster version of the pipeline and another to show visual outputs for easier experimentation purpose with different processing techniques. Here, I'm defining two functions to filter the EEG signal. One creates a bandpass filter for a given frequency range and the other applies the filter to the signal. I use this to extract the theta, alpha, and beta bands, which are important for emotion analysis. In debug mode, I am using this function to plot the raw EEG signal next to the filtered version. It helps me quickly check if the filters are working as expected for each frequency bands. After filtering, I convert the EEG signals into log-scaled Mel spectrograms. A spectrogram is basically a visual map that shows how frequency content in the signal changes over time. Mel spectrograms are particularly good at capturing complex patterns, and that is exactly what my CNN needs to distinguish between different emotions. This class handles the whole spectrogram extraction process. I use it to make sure the processing is consistent across all EEG channels. Now, to better evaluate my choice of spectrogram method, I included another visualization function. This compares log-scaled Mel spectrograms with continuous wavelet transform, the CWT scalograms. That helps me to verify my map approach visually. Now, to really get the deep insight from the spectrograms, I'm using a pre-trained model, specifically Google's Inception V3 from TensorFlow Hub. This model has already learned powerful features from millions of images, so when it processes my EEG spectrograms, it can extract very rich and meaningful features that simpler methods might miss. In debug mode, I also compared embeddings from different pre-trained CNNs, particularly Inception V3, MobileNet, and EfficientNet. This is to compare the embeddings to see which model gives more meaningful and consistent features. This helped me choose Inception V3 for the final pipeline. Then, I'm mapping the extracted embeddings onto a grid. This mapping mimics the 62-channel EEG caps which were used in the SEED4 dataset collection. This preserves the spatial structure of the data, which is very important. Then I reshape the spectrograms into a format that my deep learning model is compatible with, preserving all the EEG chunk, channel, and frequency band aligned. These two functions make it easier to work with the SEED4 data files. One builds the correct key to access an EEG event from the .mat files, and the other grabs the participant ID from the file name. I use them throughout the pipeline to keep things consistent and automated. This function loads the EEG signal for one event, splits it into chunks, and assigns the correct emotion level to each chunk. This function loops through selected events for a participant, extracts the spectrograms, generates the embeddings, and also collects the matching emotion levels. This function saves the processed EEG features and their emotion levels in my Google Drive, in this folder. This part creates a dictionary that maps each experiment group to its list of EEG file names, sorted by the participant ID. And this class wraps the full pipeline. It runs the feature extraction steps for each participant and session, and saves the final outputs for my CNN. Now, this runs the full pipeline for selected participants and sessions. In my experiments, I sometimes ran the code for less participants so that it is less resource intensive and faster. We can change it from here. To ensure the entire pipeline is reliable, I included this unit test that covers filtering, spectrogram generation, embeddings, reshaping, level matching. Regularly running these tests guaranteed that my pipelines is functioning correctly. This wraps up the EEG feature extraction pipeline component. Now my EEG data is fully structured, deeply processed, and ready to train the deep CNN model that classifies the emotions. This is the second component of my project, the emotion classification model. It takes the output from the feature extraction pipeline, those deeply processed EEG features, and uses them to train a CNN that can classify emotional states. The main model I use here is called the CNN deploy model, is the one I later export and use in the API. I've also included a couple of experimental models in this notebook, like a shallow CNN and one with spatial attention, which I use for testing and comparison. I'm not using the raw SEED4 dataset in this part, I'm using the extracted features from the previous step, but since the data still came from SEED4, I've included the dataset citation and credits here as well. Since training deep models can use a lot of memory, especially in Colab, this cell checks the available RAM. Next, I import all the libraries. And in the config, I set up the main configuration for training, the input shape of my EEG data, number of emotion classes, batch size, number of epochs, and the list of selected participants. I also define the path to the features saved to my Google Drive. Here, this function loads the extracted features and emotion levels for each subject and session. I also track which subject each sample came from. I'm not applying class balancing here. I'll do that later, only on the training set to keep the validation more realistic. In this step, I'm applying the JDisco normalization to each EEG sample individually. This helps standardize the data by reducing skull differences across samples, which makes the model training more stable. Here, I'm splitting the dataset into training, validation, and test sets using stratified sampling. This keeps the emotion class distribution balanced across all three sets, which is important for fair training and evaluation. Now I'm applying the class balancing, but only on the training set. I undersample each class to match the size of the smallest one. This helps prevent the model from being biased toward more common emotions. This is the CNN model I use for final emotion classification. It starts with Gaussian noise for regularization, then reduces the input dimensionality. After that, it has two convolutional blocks and two residual blocks to extract and refine the deep features. I'm also using dropout and global average pooling to prevent overfitting. The final dense layers output the emotion class predictions, and this is the model I export and use later in the API. I'm training the model with early stopping and learning rate reduction. The mesh model is saved to my Google Drive for deployment in this folder. I evaluate the trained model on the test set. It prints the accuracy, a classification report with precision and recall, and shows a confusion matrix for class-wise performance. It also has the F1 score and macro average score as well. I also tested a shallow CNN and a version with spatial attention. This helped me to compare different architectures, and I only use the main model for deployment. That completes the second component, building and training the CNN emotion classification model. The trained model is now ready for deployment in the next part, where I'll use it in my API to recognize emotions from EEG data. Let's move to the third component of the project, the API backend. This part is built using FastAPI, which is a high-performance web framework in Python. It loads the CNN file, the trained CNN model here, and expose it to endpoints so we can make real-time emotion predictions using EEG data. This model gets loaded once when the API starts. And it stays in memory for fast performance. Users can send EEG data either as JSON or by uploading a NPI file. And the API returns the predicted emotions, confidence score, class probabilities, and a mental health suggestion. Behind the scene, the API actually takes care of a few things. It validates the input shape, applies JDisco normalization, runs the model prediction, and then maps the result to a personalized intervention. There are multiple endpoints, one for raw JSON, one for the NPI files, and one that loads a predefined EEG sample for quick testing or front-end integration. I use that while in the development for quick testing. For every request, the API returns a clean JSON response that includes the predicted emotion, confidence, the class probabilities, a mental state level, and a mental health suggestion. I built the backend in Visual Studio using Fast API and TensorFlow, and I used UVCon to run the API locally for testing. The fourth and the final component is the UI. This is a React-based frontend, and this is the user interface where people can upload EEG data to get real-time predictions from the model. The frontend has three main parts: the file uploader.js, the prediction history.js, and the result display.js. The file uploader lets the user to choose a NPI EEG file, and if it's a batch file, select a specific sample index to analyze. Once uploaded, the data is sent to the backend and the prediction result is passed to the result display. Since this is a low-risk project, I did not collect live EEG data. I'm using the extracted EEG features from my earlier pipeline for demonstration purposes. Once the user upload their EEG data, the system lets the user select a sample index, because the NPI files that I'm using for this demonstration purpose are batch files and they contain multiple EEG data. So the user can select the specific EEG data they want to send to the backend for emotion detection. For example, I'm selecting sample number 4, clicking on analyze, and the prediction displayed and the predicted emotion is displayed on the front end. Now if I select another sample index, for example 60, the predicted emotion is displayed with a confidence score and a breakdown of class probabilities along the 4 emotion class we're detecting. Below that, it shows the user's current mental state and suggests a mental health intervention. The user can also track their last 5 predictions in history panel, which helps visualize emotional trends for the user over time. Let's try with another EEG data. And that brings everything together, from raw EEG signals to deep learning predictions, real-time API integration, and a clean interactive frontend. This system is designed to support emotion recognition and mental health awareness in a practical and user-friendly way. Thank you so much for watching.